the whole field of gravitational waves, and I'm going to sort of focus a bit more on the ground-based detectors and speak a bit about neutron star observations that we're hoping to make in the upcoming years. So thank you also to Ricardo and Per for inviting me to talk. So I'm going to go through, what are our expectations. Sathi's covered some of this already. I'll take my own spin, and then how are we actually going to do these measurements that we're talking about of the masses and so on for neutron stars and black holes in general. What kind of thing would we expect using the upcoming advanced generation of gravitational wave detectors, and where are we going to take it in future? The Sathi has given a hint about the further generation, but what can we do with just the upcoming generation, and focusing more on the more immediate horizon. So binary neutron stars are probably the most likely source of gravitational waves to be detected in the ground-based detectors, because we know that they exist. They've been observed in the galaxy, and we even have examples that will coalesce in a few tens of millions of years. So the rate expectations are less broad for these sources than they are for binary black holes and neutron stars, for example, which rely entirely on theoretical models, because no one's ever seen a stellar mass binary black hole before. So if you take these, fold in the known sources and the population models that have been done to date, you can make a sort of order of magnitude estimates of the number of sources that we would detect in the coming gravitational wave detector generation. And you can see that these actually vary by a few orders of magnitude depending on the assumptions that go into the population models. But we're hoping that somewhere between 0.4 per year in the most pessimistic case, and 400 in the most optimistic case, is the kind of range that we're looking at, with 40 being the kind of mean number in the middle. So I'm hoping that we'll get several tens of events per year in the final design sensitivity curve for these sources. So there's a run starting this year which has a reduced sensitivity, and even that has a chance of making a detection, although the actual lower limit here is very low. So we're not particularly hopeful about this year, but it is exciting to actually have the data to work with after the drought of the last 5 years. Binary neutron stars are a great source for ground-based gravitational wave detectors, because they're very well described by the post-Newtonian expansion, which a lot of you learned about in the workshop, the summer school over the last week. And this in-spiral signal, which tells us a lot about the actual parameters of the source. So it lets us do the inverse problem and recover some of those parameters using the signal. They're also interesting from a multi-messenger point of view, as Sathi pointed out, because the material in the neutron star is expected to be disrupted and emit electromagnetic radiation, which could be captured by follow-up observations from survey telescopes, for example. And also they're a prime candidate for the central engine of a short gamma ray burst. So what do we know about binary neutron stars? Well, if you look only at binaries, neutron stars that have been seen in the galaxy in binaries with other neutron stars, they actually have quite a tight mass distribution of peaking around 1.35. So in this plot here, you can see this is the canonical value for neutron star, about 1.4, but they do appear to have a slightly lower mean value, and the histogram is pretty tight. They're also observed to be pretty much non-spinning. The fastest one has a mental spin of 0.04. That's that one there, double pulsar, and this is because most of them are old and they've spun down over time. If you look at more generally neutron stars that we know in other binary systems, so for example with white dwarfs, they have a much broader mass distribution that can go somewhere anywhere between around 1 and possibly as high as 3, and this depends a lot on the actual maximum mass, and that depends on what we know about the physics of the nuclear equation of state that lets the star support its own mass under gravity. So when we're doing our searches for binary compact binaries, we typically think of binary neutron stars occupying the range between around 1 and 3 solar masses, although we do kind of hope that we'll see something at the same sort of canonical value, I think. So what is there to measure in these systems? So a binary, if we just draw a cartoon, consists of two compact objects. These are black to signify that they have no extra features. These are, you can think of these as black holes. And the most important parameters of this system are, of course, the masses of the objects. This determines how fast they spiral and the eventual frequency of the source. And also the spin of the objects. So in neutron stars, this is likely to be quite small, but in black holes, it can be larger. And that can also modulate the waveform that you will see, as I'll show you in a minute. But particularly, we measure not so much the individual masses, but this combination of the masses that we call the chirp mass. So if you see written in the later slides, chirp mass, what it refers to is this funky combination of the individual masses that determines the overall phase evolution of the binary, in a sense, to the lowest order. And then the other parameters are corrections on top of that, basically. A lot of you, this will be familiar. As well as the sort of masses and spins, there are also extrinsic parameters, as we call them, which are more to do with the location, the orientation of the object. And this can tell us stuff about, for example, the distance to the source. We can measure that quite well with gravitational waves because they're very well understood how they propagate. But also the inclination angle, for example, is of interest. If you're looking at binary neutron stars, you would expect that if this was a gamma ray burst, you would expect the beamed emission to be along the axis of total angular momentum, basically. Now, if we make things a little bit more complicated and add matter into the picture, you can make the models more sophisticated and include things like the equation of state for neutron stars. You can see here they're now being deformed by their own tides. And also, as Satya touched upon, and Walter will talk about a lot more, deviations of the waveform from those predicted by general relativity. And then there are higher order effects like residual eccentricity, which is expected to be quite small, but I think it's worth putting a limit on that if we can. That's limited at the moment by developments in the waveform modeling, I think. Okay, so that's what we're talking about here. Satya touched upon the noise curve evolution. I just wanted to say that this is an ongoing process. At the moment, we're commissioning the detectors. Advanced LIGO is the one that's expected to come online this year, with Advanced Virgo following later, next year or 2017. And over the course of the next 4 years, these noise curves will get lower as the detectors improve. You can see how well the instrumentalists have been doing in the last few months by looking at this evolution. As we kind of gradually get down to the kind of 01 noise curve. 01 is the first observing one that will happen this year. And if you put that on this plot that a lot of you will be familiar with, this is the little sphere in the middle is the initial LIGO sensitivity. And even in May this year, Advanced LIGO Livingston was able to cover this much larger volume. If you think about, you know, your horizon distance, your radius is larger, but that means your volume goes as radius cubed. So the rate estimates will go as this circle cubed, basically. And already we're starting to fill up this large blob, which will be the expected range of the final design sensitivity of the advanced detectors. And I just wanted to point out this is a very exciting time for us because the first observing run at somewhere around this level is going to start in September. So we're bound to have some data to analyze and some new upper limits to set very soon. Okay, so let me get some water. How do we actually get the information out of these signals then? Well, the waveform itself is a function of the component masses of the system and also the extrinsic parameters we saw. And this carries away information encoded in the structure of the waveform. So if, I don't know if this will play if I press, you can hear the audio frequency of the sound, and this, the actual waveform that's observed in the detectors will be modulated according to its position, frequency evolution, and so on. So it's like a radio wave in a sense that the modulation of the source carries the information about it. But how do we get it out? So we have to solve, we first have to detect them. So Satya said a little bit about this. I just wanted to point out how we do it. So if we have these known noise curves, for example, this is as an earlier run. What we do is we take the waveforms that we expect and we filter them against the data. So if you have, you can write down the statistics as thinking of it as a noise distribution, a Gaussian noise. You know what the variance is, the power spectrum gives you that. And then you can subtract the signal that you expect and look at the residuals to get statistics on how likely it was that that source was actually in the data. And that comes down to effectively convolving the expected template with the actual noise. So in this noise here, I don't have the audio for this anymore, but there is a signal buried in here, and in fact it's that signal. And if you were to convolve the known template with this noise, even though you can't see it, when you look at the output of the convolution, you get a large spike in the signal to noise ratio at the time of the end time of the waveform, basically. So going beyond detection, I mean, once we've detected the event, then we have to do this, estimate its parameters, and for that we use a Bayesian inference method, which again a lot of you learned about in the summer school, which lets us write down a probability distribution for the parameters of the source. That's a function of the data that we see, and also on our prior expectations for those parameters are. And again, you have the same likelihood function that we saw before, where here the waveform model is not just a function of the masses, but also the position, orientation, and so on of the source. So that lets us, with this more detailed model that does include all these extra effects, we can then solve this distribution to find our statistical errors on the estimates of the parameters. The actual number of parameters, as we saw in the earlier slides, it can be up to 15 if you include the spins and their orientations, as well as the masses and positions. And if you want to include things like the equation of state or deviations from general relativity, this can get much higher dimensional again. So it's quite challenging to actually solve this inverse problem. So the question is, you know, I said it's difficult to solve this so in full, but there are approximations that you can make to speed up the process. So for example, we have now in the collaboration a rapid code that will only estimate the position of the source on the sky, because we want to send alerts to electromagnetic telescopes to follow up the signal on timescales of, you know, less than a minute ideally, but also later on when we have more refined estimates of the position and so on, there are other afterglows that can be followed up on timescale of hours and days. So there are different schemes to do this, starting from the rapid localization, going on to the more detailed modeling that doesn't include the spins, and then moving, finally the slowest code will come from those that have the most detailed waveform models, because those are most expensive to calculate. To actually compute these posterior distributions, we can't just grid up the parameter space, because in 15 dimensions the number of grid points is enormous. So we've developed a bunch of different methods to sample this posterior distribution, and then when you want to look at the result, you just make a histogram of the samples. So for example, here is a histogram of a chirp mass for a binary black hole, and then using these samples you can set confidence intervals, standard deviations, so on of the estimates, but also use the samples as input for calculating additional inferences on multiple sources using Monte Carlo integration. So these are a proxy for the actual parameter, the full distribution. There are two main methods that we've been using over the last few years. The first is Markov chain Monte Carlo. It's just probably quite familiar to some of you. How this works is that you start with a random point in parameter space and take a random walk around in the parameters. And if you go find a higher likelihood point, then you keep it. If you don't find a higher likelihood point, then you throw it away. So gradually your random samples will converge on the distribution that you actually want to sample from, which is the posterior distribution for the sources in our case. So you can see here that there's a Markov chain that starts off in a random place and locks onto the actual distribution. And if you look at the histogram of these outputs, then you see that you get nice peaks at the true values. The other method that we've been working on is called nested sampling, which is more useful if you want to calculate marginal distributions. So this is sort of similar. It starts with many samples from all over the parameter space and gradually eliminates the ones that have the worst fit to the data. And as it does so, you can see the remaining points that are the red ones get more and more concentrated on the actual peak of the distribution. So as you narrow down the volume of the parameter space, you increase the likelihood, and at the end you see that the red points are actually locked in on the true mode of the distribution. Excuse me. So it's not easy to implement these algorithms in these dimensional parameter spaces. So we've taken the approach of multiple implementations using these two different methods basically, and we can cross-compare them to ensure that we're confident in our results. So this has been an ongoing challenge over the last few years, is making sure that we can actually agree when we do get some simulated sources. And we've reached the point that we're pretty happy with the resulting code. It's called law inference. And this is now basically a workhorse for doing simulated studies for sources and also providing a basis for more advanced investigations of the type that you'll hear about tomorrow. So I think at this point we're ready to go. We're prepared for the first observing run to do the basic parameter estimation, as I'll show you. There are some complications. The different ways of computing the waveform, depending on which expansion you use or what type of physics you want to include. And these will lead to what we call different approximates to the true signal. And there are a range of these, ranging from the kind of most accurate ones that tend to be solving differential equations in the time domain, where you evolve the orbit of the binary and carry along its spins and so on. The most sophisticated, I think, is the effective one-body systems that Alessandro was talking about last week. Now, these are very slow to compute, so there are alternative waveforms that work in the frequency domain. For example, the stationary phase approximation that Ricardo talked about yesterday. This is probably our fastest one, and then there are approximations on that include physics of the merger and the ring down that you'll hear about later in the week as well. So I won't talk too much about them. So for simulations so far, I mean, we've done some studies with populations of binary neutron star simulations, and I wanted to show you sort of what we're going to expect to see for when we do eventually make a detection. So these were most of these results come from a data set that we worked on recently over the last few years, and it's resulted in a few papers that I'll refer you to for more details. But what we did is take an astrophysical distribution of neutron stars, but a much more amplified rate, so we have a large number of events to build statistics on. And we took the noise curve for the expected run that's going to start in September. So this should give you an idea of the results that we could see this year if we do make a detection, or next year if we use the improved noise curve and include Virgo in the analysis. So I said there were two different methods for doing these sky localizations and sending rapid alerts. There's one that's very fast and one that's a bit slower. So the first result is that when we only have two detectors, as we will in September, just the LIGO detectors will operate then. The good news is that there is essentially no difference between the rapid and the slow codes. So the rapid code does not, I mean the slow code, it refines the sky location slightly, but the difference is basically negligible from the point of view of anyone doing electromagnetic follow-up. So the actual error boxes that we're going to broadcast will be pretty refined. There's not much more we could do in the two detector case.
This rapid method would not use
For the 2016. So let me explain what Safi is mentioning. So you see in 2016 there's a difference here between the fast and the slow method, because the fast method can only use the triggers that were observed in detectors. And in many cases, Virgo, with its slightly lower sensitivity, will not produce a trigger. So you will basically have a set of events that only are measured in 2 detectors rather than 3. So the problem is that there's no way of incorporating, well, there is a way, but it's not implemented, a way of incorporating the information from the 3rd detector when you're producing the rapid localization estimates. So what you would, I think I know how to do it, but it would then slow down the latency of the low latency code, which you have to integrate over the unknown event in the other detector. Well, probably a factor of 10, I would say. Now, there might be some clever tricks you could do. I'm just thinking off the top of my head, but yeah, I think when it comes to 2016, we can start moving in this direction. But for this year's results, I think we're in good shape. Right. I should explain the axes, shouldn't I? Yeah. So the on the x-axis is the number of square degrees for the 90% confidence interval, and you can see that if you look at the median event, for example, here, the number is actually very large. It's almost like several hundred square degrees. So you need the very wide field cameras to try and do this follow-up. Are you asking about the normalization? Sorry. Yeah. Well, these are normalized to basically the same scale. So this number here is much larger than this number because there will be more detections in 2016 from our simulated data set, basically. Does that make sense?
So it is relative to the number we can observe in a single detector, right, at the design system like the volume, high volume.
Yeah.
So on the left, one means that we expect one event will apply vector 500 square meters.
Well, it's a cumulative distribution. The normalization is kind of irrelevant, but the idea is that these are kind of on the same scale, even though they're not normalized in an obvious way. Okay, so then if you narrow things down using the 3 detectors, you get this better triangulation. If you think about it, if you take 2 microphones or detectors, you can measure the time of arrival of the source in 2 positions, and that gives you a ring in 3-dimensional space of possible origins for that source that will produce any given pair of arrival times. Now, if you add a 3rd detector to that network, that breaks the degeneracy on the ring and lets you narrow it down to only 2 points above and below the plane of the detectors that's formed by a triangle. So that is the reason for the much greater improvement here, as well as the improvement in the signal-to-noise ratio. You have a vastly better measurement of the time of arrival because of the 3rd detector. And you can see that, for the 2 detector cases, it's actually not as different as it would be otherwise. Okay, how am I doing for time? Okay. So these simulations were done with Gaussian noise. I just wanted to point out that we did repeat it with basically a proxy for real detector data, which is very noisy and has a lot of strange chirps and hiccups in it. But effectively, the sky localization position doesn't change very much, so we're quite confident that we'll be able to produce good results if there is a real signal, even in the presence of non-Gaussian data. Now, moving on to the other parameters, there's the question of measuring the masses of the neutron stars. This isn't quite so easy as you would perhaps hope, because if you look at the 2-dimensional distribution, here we've got M1 and M2, M1 being the heavier one, M2 being the lighter. You can see that the chirp mass parameter that I mentioned earlier is very well measured, because that's what determines to zeroth or the phasing of the binary. And that will basically constrain you to a banana shape in this parameter space. But then the mass ratio between the 2 signals is much more poorly measured, because it's a higher order effect on the waveform. To make matters worse, if you include spins in your analysis, there's a degeneracy between the measurement of the spin of the system and its mass ratio. And that will basically further broaden this degeneracy in the parameter space. So here you can see that for a variety of signals, they each have their own banana. And then in the notches here are the limits at which if you assume that the spins must be less than some value, which for neutron star you might say, well, they're basically 0, then that will show you the limit of this banana. So you can see here, if you assume that they're non-spinning, then you'd get this area. If you assume they have a spin of less than 0.4, which is probably quite reasonable for neutron stars, you would get up to here. If you allow the spins to vary all the way to 1, which is the maximal spin for a black hole, then it gets much broader. So the picture is really...
On that plot, the real signal is with the sun signal.
Yep.
Why isn't there something on the right-hand side as well?
You mean down here?
That's the equal mass, I understand.
Yeah.
Almost all your signals were injected in the equal mass case, but except there's one which has a slightly larger mass. I think the third curve, yeah, that one. Why isn't there something like that?
You mean down here?
Yeah, when the spins are 0.
Oh, there should be a limit on this side. I think it's basically symmetric about this line, so it's not so interesting.
No. If it is really symmetric, then it should be before it.
Well, it's symmetric if you swap the labels and the objects. What is not symmetric is whether you add the spin or subtract it, right? So that it correlates in one direction with the mass ratio, but not in the other. Well, in the other direction, your mass ratio limits things, so it can't have as big an effect, basically. So the picture is not symmetric in the direction of the spin or in the mass ratio. I can't remember exactly which way the correlation goes at the moment, but we can talk about it later. Okay, so another way of looking at these results is to sort of show you what the standard deviation would be in the total mass as a function of the cumulative distribution of all these sources. If you look at the spinning case, you can see that this is actually basically an order of magnitude worse for the total mass. Yeah. In the Q parameter, which is the mass ratio, you have a similar picture. So this is basically what's limiting us from making an accurate measurement of the mass. So what we would like is if there was a confident astrophysical model that could really limit the spins, but I don't know if we're that confident at the moment about these things because we're quite conservative about what we're going to look for. I think once we've seen a few sources, I expect that they will turn out to have low spins, and then we'd be more confident in making these assumptions in future follow-ups. Oh yeah, a spin of 1. I think a spin of 0.4 is probably what you would realistically expect to be the maximum, because the neutron star will break up long before it reaches 1. But nonetheless, you would probably want to do the analysis with all of them anyway, because they could be sub-solar mass massive black holes. Okay, so that leads on to the question of how well can you measure the spin. For neutron stars, basically all of our injections had very non-spinning sources. You can't actually constrain the spin very well for the same reason that you can't constrain the mass ratio very well, because it's degenerate. Nonetheless, in the heavier body, you do get slightly favored the non-spinning side of things. For the lighter body, it's more difficult because the majority of the modulation comes from the heavier mass. Nonetheless, you can see that it's slightly tilted. But really, you have to look at black hole systems where the spin is highly important in the modulation of the waveform to make better measurements. I think Salvatore is going to talk about that later in the week for black holes. Yeah. It's very low spins anyway. It's like less than 0.04, so it's basically on this spin equals 0 axis. Matt? Oh, that wasn't a question. Okay. Let me finish over. So there are additional challenges in the modeling. As I said, there's multiple models and they each lead to slightly different results. This is probably a pessimistic picture because it comes from a paper of a few years ago and things have improved since then. So we need to repeat this study to see what kind of systematics we would get using modern waveform models. The final thing I want to talk about is, when we start making regular observations, how are we going to use them to do astrophysics? And this sort of touches upon stuff that will be used in, measuring deviations in GR, but I just want to talk about a few examples. So what we're planning on using is something like a hierarchical model, where you have parameters that govern the population of sources and their common physics, for example, the equation of state. And then each actual individual source is drawn from that population, has a particular realization of it. So you can, using the same sort of Bayesian inference techniques, you can eliminate the uninteresting parameters for each source and learn something about the parameters of the global model. A good example of that is the equation of state, which Sathya mentioned earlier. There's uncertainty about how matter behaves at these supernuclear densities. And that determines basically the radius of the neutron star. And that also feeds into how deformable it is. So if you think about two neutron stars, when they reach the end of the in-spiral, they're moving very fast, but they're also very close, and they start to deform each other in their tidal fields. And that actually has quite a significant effect at high frequencies, although not so much at low frequencies, by modulating the phase of the in-spiral. So you have your point particle part that we've learned about from the stationary phase approximation, and then you can add on these corrections that come from the response of the neutron star to the tides. And the idea is that by looking at this deviation from the point particle, you can put limits on the equation of state itself. So this is the relationship between mass and radius in the phase diagram. And so here's an example from work that I did with Walter and others at NICHEV on distinguishing between three kind of example equations of state. You could say soft, medium, and hard, depending on the stiffness of the material. You can see that with a single source, your error bars are very broad, and you've got very little hope of actually measuring it. But because we can amplify the effect by looking at many sources as the number of detections starts to build up, the error bars that represent 95% confidence regions start to home in on the true values. So you can see that when we're able to make multiple detections, there's a lot more that we can do over just looking at individual objects. And the same will feed through to other work that we'll talk about later. Examples being binary evolution, which I'm going to skip because Sathya was talking about that. But again, we would like to know more about how these systems are formed in the first place, and we can start to do it by looking at multiple populations. An effect that I'm worried about myself is selection bias, because we do, have preferential orientations that emit more gravitational radiation. We also have a selection effect because the highly spinning, highly processing systems are more difficult to detect with a search pipeline, and that can feed through to the overall estimates of the parameters that you would see when you try and measure the total distribution of sources. Okay, I'm going to just finish up mentioning gamma ray bursts. Again, you can do a similar population study looking at not only the gamma ray bursts that you do see, but the ones that you don't see, or rather, if you do detect an in-spiral but you don't see a gamma ray burst, that tells you that the axis must have been misaligned with the gravitational wave axis. Not the gravitational wave axis, but the view direction of the source. So if you see enough compact binaries in gravitational waves, you can put limits on what the beaming angle must have been, because you would expect basically to see the fraction of events in gamma rays that you do in gravitational waves related to the beaming angle of the source. So that's an interesting point to come across. There are also challenges with modeling the non-Gaussian parts of the data, which I'm not going to talk about just now, and further improvements to the code. But let me just finish by giving you an overview of the outlook. We're very, after a lot of work, we're ready to go. We're kind of raring to get the data this year. and very excited about making detections in the next couple of years, I hope. And we've got pretty confident about our ability to measure the source parameters modulo the systematic bias that comes from waveform uncertainties, which actually may turn out to be less than we think. In the future, I think things are going to go in the direction of developing methods of combining multiple sources, how to identify the counterparts and the host galaxies of those sources, because you really want to do these multi-messenger studies that Satya mentioned as well. And those carry their own difficulties because there are a lot of uncertainty in the astrophysical models. So how do we actually parameterize those in a way that we can start to constrain them with gravitational waves? Okay, so I'll finish there, and we can just move over to questions / coffee time, I think. Thank you.
Could I ask a general question about the parameter distribution? You mentioned about the last one slide, improving the efficiency of pipelines.
Yeah, yeah.
So how much gain computing efficiency is there to be had?
There's quite a lot. There's two ways you can do it, right? You can make the codes faster in themselves, so if you can generate templates faster. Yeah, okay, so not spreading them over multiple nodes, which I think is probably going to be the way to go in the future. The amount that you can squeeze out of waveform generation there's still another couple of orders of magnitude, I think, because
Just the parameter distribution itself, is there anything more? I mean, there have been so many new things that have come out, such as going from CMC to reversible jump and nested sampling. What more? What else can you do?
I think the way forward in that side is to make them much more parallel. And we're working on that at the moment. That should hopefully let us spread the load over more computers and get results faster.
Yeah, I was just wondering, considering if you really wanted to look at it and spins and obsession and how cost it is there any benefit from doing some kind of hierarchical counter estimation first start core surface, then pinpoint and then go down instead of punishing every?
In a sense, we do that, but not. So we do measurements at different levels because we want to get intermediate results faster. Then if you you can use the output from the earlier results to start off the estimation in the more advanced ones. But actually that doesn't help a huge amount because most of the time is not spent looking for the signal, but is spent on getting enough samples from the distribution. So once it's converged, you still have to let it run for basically another order of magnitude. It spends maybe 10% of its time locking onto the source and then 90% generating enough independent samples to give you a proper idea of the confidence intervals and so on. Yeah. Well, you could do something like take a fixed value of the masses and then you can place estimates on the spin maybe a more rapid way. It's not something that anyone's worked on immediately, I don't think, but it's an interesting question. Yeah. Yeah.
I don't know if you're, I mean, the problem is you can parallelize, but we're already hitting computing computation costs. I think you should parallelize, but it might, the answer can only be more computers. Some kind of hit a wall.
Well, there are smarter ways of doing things even with existing computers. I mean, people are looking at these reduced order models and reduced order integration schemes. I think that's going to help a lot as well.
I was hoping you would mention, sorry, just a quick one. These interpolation methods.
For the waveforms.
Even the likelihood calculations.
Yeah, yeah. So the idea is that you don't have to compute the integral by integrating over frequency, but you can have a different basis function, a set of basis functions other than frequencies. And that way you can calculate the same integral, but with using a smaller number of computational cycles, basically, if you weight it appropriately.
In one
Well, no, I was referring to more accurate than the ones that don't include merger ring down, basically. They don't include the merger and the ring down. I think there's I don't know the answer to the question of whether EOB is more accurate than IMR for non-P, and I refuse to be drawn on that at the moment.
Just to follow up on I saw the numbers involved in the MC and other method. There
Uh-huh.
are about 300,000 trials.
Yeah, yeah.
Now, that seems to be a large number for a kind of a polynomial problem. Now, what would be the efficiency in evaluating or using the waveforms for each of the steps that you will need to be realistic, computation? If I understand that, it would be very expensive.
You mean how fast do you need a waveform to make this work? Like order of 10 microseconds or less per waveform. I think that's the ballpark that we talk about, right? Correct me if I'm wrong. Yeah.
Because of fastest waveform.
Yeah, I mean, you can, yeah. I think these reduced order models are really helpful, right? Because they let you take the full physics waveforms, the full fat waveforms, and produce a reduced version of them that can be calculated in a few milliseconds.
This is a very general question. Is there hope of extracting parameters from the electromagnetic signals?
Yeah.
In a way that then either A, not projection, or B, basically degeneracy?
So there's work on kind of doing joint searches. For example, I'm working with some people who work with Fermi, and you can take not only the Fermi, things that they put a gold stamp on and say these are gamma ray bursts, but look at their raw data and see for their subthreshold events whether you can do combining the LIGO data with Fermi data. You might be able to improve your detection efficiency, and I think in principle you should be able to. There's still some sort of technical details that need to be ironed out, but I'm hoping that will be a useful way forward in the future as well. And that, because there's not the full information from Fermi, but only really the the small number of counts, basically. You have to do more sophisticated joint statistics with both sets of data. If you have a counterpart, like if you're triggered on a gamma ray burst, so another thing I didn't mention is that if there is a gamma ray burst that's detected, then we look at that specific data around that time with actually a more sensitive search code, because we can target the position very accurately. And also because it's a smaller time stretch, we can use a less computationally efficient method. So that lets you improve the sensitivity by a factor of something like 1.5, I think, for Steve's work I'm talking about. And then also follow that up with more targeted parameter estimation as well.
For binary systems, it's more like 20%, 30%. Whereas for bursts, it's more like 50%.
Okay, there you go. Yeah, I didn't mention the other unmodeled approaches at all. I don't know if anyone's going to cover that.
We're standing between these people and coffee. So, just some comments. The coffee, I presume, is up there. And we're only 5 minutes late. That means, in principle, 25 minutes. If we get back here at 12, we'll be back on 9. Just going back to lunch. So we're reconvening at 12.
What has happened here? Thank you. Little help. Who's after me?
She's going off to get her.
How do people measure neutron stars mass? I mean, isolate the neutron stars.
So, for isolated neutron stars, you basically can't. They have to be in a binary system, because then you have the possibility of measuring orbit. And if you make some assumptions about the possible masses of white dwarf, say it's about a neutron star, white dwarf system, for example, then by looking at the actual optical period, you can predict where the mass of the two objects, and that gives you some uncertainty, which is why there are error bars in those systems.